Hello students, so today we will do some problems on electrodynamics. We'll first start with a problem where there are four equal point charges which are kept fixed at four vertices. It's actually not electrodynamics as well as electrostatic problems. We'll consider both. Now, these 4-point charges are, for example, they are kept at the four vertices of a square, and these are the 4-point charges. And so the question is, there are how many neutral points are there or exist where the electric field is zero. How many points are there? The field is zero. And the answer is inside the square there is only one point, that is at the center, where the electric field is zero. So the answer is 1, that is at the center. The second problem is a static charge distribution it gives rise to an electric field which is given as E is equal to alpha 1 minus e to the power minus r by capital R to the power r by r square. This is the point vector, and where these alpha and r, these are positive constants, and it is a sphere, considering a sphere whose radius is r. So we need to find out the charge distribution contained inside the sphere of radius r. So here we would like to find out the Q enclosed inside the sphere. Now to do that, we need to first use the Gauss's law. It states that Q enclosed is equal to epsilon 0 integration E dA, and so putting the values of the electric field, it turns out to be alpha epsilon 0 integration 1 minus E r by r by dot, this is for the E part, and dot the area is r square sine theta d theta d phi and dr. So it is then equal to again alpha epsilon 0 to pi and 0 to 2 pi. Converting into spherical coordinates, it is 1 minus e to the power minus r by r. So this r square and this r square cancel out. It's cancellation of these two, and so we are only left with sine theta. So here it is sine theta d theta d phi. So at r is equal to r, this reduces to enclosed, it reduces to alpha epsilon 0 to pi 0 to 2 pi 1 minus 1 by e d theta d phi, and it is equal to alpha epsilon 0 1 minus 1 by e into 4 pi. So the answer is 4 pi alpha epsilon 0 1 minus 1 by. This is the charge enclosed within the sphere. So move on to the next problem. The next problem is if you consider a solenoid of radius r with n turns per unit length, having n turns per unit length, means this is the solenoid. Now in this solenoid, a time dependent current, that is I is equal to I0 sine omega t is applied, and it is given the condition that omega r by c is much less than 1, and you need to find out the magnitude of electric field at a particular distance r, which is much less than r, from the axis of symmetry of the solenoid. That means if this is the axis of symmetry, so for that we will use that E dot dl rate is equal to minus rate of change of magnetic field is causing the electric field dot dA. Now we know that del cross E is equal to minus del B by del T, the induction, Maxwell's law for induction. and so we will replace this del B by del T by del cross E. So the equation changes to E dot dl is equal to del cross E dot dA. Now here the magnetic field applied B is equal to mu 0 n I function of time in the z direction. So putting these values, we ultimately get that E dot 2 pi r, that means E dot dl is equal to E dot 2 pi r, and so E dot 2 pi r is equal to mu 0 it is again equal to minus mu 0 n I 0 omega cos omega t dot 2 pi r square by 2. So this is actually coming from del cross E dot dA, the value that we are getting, and so putting all these values, we get the value of E as E is equal to minus 1 by 2 omega mu 0 n I 0 r cos omega t, and this is the required electric field that we were searching. Okay. So coming to the fourth problem. The fourth problem is a constant current I is in an infinitely long straight wire. Is suddenly switched on at say time t is equal to 0. So we need to find out the vector potential, which is A, at a particular distance r from the wire. And this vector potential is given as A is equal to K mu 0 I by 2 pi into natural logarithm 1 by r Ct plus c square t square minus r square. We need to find out the electric field. Okay. So for that, what we have to do, the electric field at a distance r, we need to find it out. So this electric field E is again is equal to minus delta phi minus del A by del T. This is the scalar potential. Scalar potential, this is a vector potential. So we put the values of those things. Electric field comes out to be minus C mu 0 I divided by 2 pi C square T square minus R square into K. This is done. The fifth problem, it says that the magnetic field corresponding to the vector potential, there is a vector potential given as K is equal to 1 by 2 F cross R plus 10 by R cube into R vector where F is a constant vector and we have been asked to find out the magnetic field. Corresponding to it. So from the relation B is equal to del cross A. So and F is equal to FO X plus Y plus Z. So first of all, F cross R is equal to X, Y, Z, FO, 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 X, Y, Z, and it is equal to then X Z minus Y 4 minus Y Z minus X 4 and plus Z Y minus X. So del cross F cross R it is again equal to X, Y, Z del by del X by del Y and del by del Z, and here it is FO X minus FO Z minus Y. It is FO X minus Z and it is FO Y minus X. And so it is equal to X FO plus Y FO plus Z FO, and it is again equal to then FO x plus y plus z. So we initially started with the vector which was E was given as half f cross r plus 10 by r cube dot r, and we know that B is equal to del cross A. So by the first part, the answer comes out to be equal to FO or F, and del cross r by r cube is equal to 0. So we are getting B is equal to del cross A is equal to only F. So this is the magnetic field that we are looking for.